Hi, everybody. Welcome to the AIA South Carolina HSW Procrastinator series of webinars. We've got a great one here scheduled for you this afternoon. Dustin Albright, Brandon Ross are going to be discussing the integration and circularity in mass timber floor systems. So I'm going to just let them introduce themselves and jump right in. Thanks for being here.
Okay, hi everyone. My name is Dustin Albright. It's great to be part of this webinar series. I too am a procrastinator, so I resonate with this group. And I'm joined today by my colleague Brandon Ross, and we're going to talk about mass timber and floor systems and acoustics. So for those that I maybe haven't met, I am practicing architect here in South Carolina. I work in the Clemson office of Hanbury. And I also am full-time an associate professor in the School of Architecture at Clemson. And Brandon, my colleague, is a professor in the Department of Civil Engineering here at Clemson. Anything else that you want to say by way of introduction, Brandon?
Sometimes I look a little more stylish so I can pretend I'm an architect.
There you go. Perfect.
There you go.
So together we are a part of the Wood Utilization and Design Institute at Clemson. And so this is a cross-disciplinary um, uh, group of people that collaborate on research and teaching. And so you see several of the participants, contributors there from forestry and civil engineering and architecture to environmental engineering and chemistry and whatnot. So it's a great team and a really highly collaborative setting. And so really rewarding to be a part of this group. And so the project that we are going to share has been connected to the Wood Institute since we were awarded the project from the Department of Energy. So the learning objectives today include the following. So you all will learn about the overarching environmental benefits of mass timber construction. You'll learn about the importance of end-of-life circularity for mass timber building components and how the system that we're going to present, the HMT floor system, is designed for this possibility. Participants are going to learn about the acoustic sound attenuation, related building code requirements. Maybe that you know a lot about that just through your own practice and experience. But we'll talk about that relative to floor assemblies and the work that we're doing here at Clemson. And then you're also going to learn about standardized testing procedures for the measurement of acoustic performance. So Brandon, I'm going to turn it over to you to describe just an overview of the project for the next few slides. And you let me know when you want me to advance the slide.
Sure. Yeah. So we took an existing idea and we'll give you a little bit of background about more of what we've done here, as Dustin mentioned, and formed a team. We have myself, a structural engineer, and a couple of my civil engineering colleagues, Dustin, an architect, and we also have Dr. Pat Layton, who's a forester on the team, as well as an environmental engineer to do some of the LCA. And I always get this question: why is the Department of Energy interested in funding the development of a wood floor system? Mostly I get that question from other people who do work with the Department of Energy. And so if you go to the next slide, Dustin, one of the missions of Department of Energy is to reduce atmospheric carbon. And so that's where this program was birthed. So it's Department of Energy, and then ARPA-E, and then under that is HESTIA. And so that's a program that with projects that last about 3 years. I think it was about $45 million total, not certainly for Clemson, but spread out across many projects. And the idea is, rather than building materials that require carbon to go into the atmosphere, let's turn that on its head and let's invest and do research in building materials that sequester carbon. And there's a really old technology that does that very well called trees. And so that's where our project came along. But there's, other folks looking at insulation or negative carbon cements they're even trying. So lots of different things there. Yeah, I mentioned some of our team there. A lot of these folks, you just saw their pictures as part of the Wood Utilization and Design Institute. And then right there, the plus at the bottom and all the small names are all the graduate students that are working on this project and doing a lot of the heavy lifting. So it's been fun to have just such a diverse team with lots of different perspectives and backgrounds all coming to bear on this problem that is inherently very multidisciplinary. So
Great,
back to
thanks,
you,
Brandon.
Dustin.
I'm
Yeah.
going to just talk through just a quick overview of mass timber. It may be that many of you have, whether it's through other webinars, material that you've read, or your own professional practice, you may be quite familiar with mass timber. Others may be still kind of learning about it. Mass timber describes, kind of overarching set of products that are large in their scale and format and are designed to be competitive with steel and concrete, construction for larger and larger buildings. And so in terms of the panelized products, the ones that I have here sort of in the boxes, the blue boxes, they are the ones that are most typically used and are available in North America. So that's cross-laminated timber, CLT, glulam, which can be panelized. Of course, glulam often is used for beams and girders and columns and linear members framing as well. Dowel laminated timber, nail laminated timber down in the bottom right, mass plywood, which is just plywood sheets that are laminated together. One product that's not represented here is that's new on the scene is called veneer laminated timber, VLT. It's produced by a company called Boise Cascade. This is just a partial map of the producers across North America. And then there are European producers whose prices are still, at least on the East Coast, for projects are still pretty competitive and oftentimes enter into this kind of the bid um, um, structure for mass timber projects. Just some of the motivating factors and advantages of working with mass timber. And, on the one hand, there's robust and resilient construction with what is a renewable natural resource, wood. The mass timber construction supports state and regional forest economies. It affords very low carbon footprint compared to steel and especially compared to concrete. And then also the opportunity for carbon storage. We'll talk about that in just a moment. Rapid construction with precise prefabricated elements, as with other prefabricated systems. High strength to weight ratio. So in other words, wood is really, really strong with respect to its own weight. And so the net sort of result of that is lighter weight buildings that can result in lighter foundation systems. The ability to expose the structure as a finished material is really appealing and can, when that's possible, it can cut out on the need for other finishes, for example, ceiling finishes. And so that saves on construction costs and time. Adaptability and circularity of the components is something we're going to be talking a lot about. Performative benefits, the inherent R value with timber, biophilia and other health-related benefits. I don't have time to get into that, but there's a lot of research out there on that. Let's talk about the environmental benefits really briefly. Environmental benefits include the renewability of timber when it's sustainably managed, favorable life cycle assessment metrics, in particular low embodied carbon. Then the fact that wood sequesters carbon, we'll talk about that in a moment. And then the natural insulating quality. So an R value somewhere between 1.25 and 1.4 per inch just for softwoods before you even add other insulating materials. So wood as a commodity, as a resource, is renewable, provided that it is sustainably managed through best practices and sustainable forest management. And so there are various organizations, agencies that you're probably aware of, like the Forest Stewardship Council, SFI, others that certify the sustainability of the sustainable management of forests, forest lands. And so something you may not know is that pictured here in the middle of this graphic, that's in orange, that's Clemson University campus. But in green, to the north and the south of the campus, it's 17,500 acres that Clemson University owns and maintains of forest land. We call it the experimental forest, Clemson Experimental Forest. All of that property is certified through the SFI Sustainable Forest Initiative system as sustainably managed. Life cycle assessment, it's imperative that we think about the whole life cycle of our buildings and our building materials. So there are various different impact categories that are included here. One that we're going to talk mostly about is global warming potential, and that relates to this topic of embodied carbon. And so when you look at this is an older graphic, so the statistics may be just a little bit different now. But this was taken from the Architecture 2030 initiative. And so this graphic dated back to 2018, at which time buildings together added up to around 39% of the total global CO2 emissions annually. And that 28% is related to building operations, and then 11% is related to the energy that's embodied in the building materials and construction. So that's a really significant percentage, 11%. And so the majority of that embodied carbon it comes into play in the building's foundation and the structure. Okay, so some is in building systems, finishes, et cetera, but the bulk is in the structure. And so as we think about mass timber and other structural systems, we have the potential to make a really big impact when it comes to reducing embodied carbon in our buildings. And why is that important? As we think about meeting carbon emissions goals, as we think about in particular, trying to think through carbon neutrality as close as we can get in our buildings, new buildings, by 2030 or thereafter. This graphic really gets at that. So a building built in 2020, it takes around 30 years until 2050 here before the operational carbon actually then outpaces or overtakes the measure of embodied carbon in the building. And so if we're wanting to pursue carbon neutrality, we really have to think about building materials, structural systems that are low in embodied carbon on the front end to make an impact in the short term. And so when
Justin,
we talk about yes, go ahead.
On that point, I'm just thinking about my career as a structural engineer. So early 2000s when I started, it was like structural engineers add some fly ash into the concrete, pat yourself on the back, and you did your part for sustainability. Just because the operational was, significantly larger. But as those energy codes have, changed, and it's a real exciting time to be a structural engineer where we can make a contribution and make a much bigger impact on it. And so within our community, there's been a lot of movement on looking at embodied carbon. So
yeah, that's a great point. And this graphic really speaks to that in that, there were all of these strides for the last, I don't know, 2 or 3 decades on more and more energy efficient lighting and systems, all the things that relate to reductions in operational carbon. And as our buildings have become more efficient in those areas, it means that a greater percentage of the overall carbon footprint is associated with the embodied carbon. And so as we think about embodied carbon, so yes, certainly the thing that I think makes the most sense is it's the carbon that's a part of that comes into play through the harvesting of the raw materials, the production of the products that go into our buildings, the shipping, the construction, et cetera, everything to get you up to the point of occupation. But there are these other areas of embodied carbon, so like maintenance and repair. That's considered to be embodied. It's not a part of the operational energy use. It's related to the building materials themselves, and then importantly, the end of life. So once the building has reached the end of its service life, or once it's experiencing a substantial renovation, what happens to the building systems, the structure in those cases? And that's something that's really integral and important for our particular project. One thing that I've mentioned just in passing before, but it's important to remember here, is that wood, as it grows, as trees grow, as any vegetative material grows, it's fed by the soil, it's fed by UV light and water, but also by the atmosphere. And so it takes in carbon dioxide, CO2 from the atmosphere. And about 50% of the dry weight of wood is actually a sequestered carbon. So trees breathe in CO2, store the carbon, and then release breathable O2 into the atmosphere, as we all learned when we learned about photosynthesis in school. Mass timber has really grown in terms of its foothold in the industry and the rate of adoption. Here you see this exponential graph here on the bottom left-hand side, dating back to like the early 2000s, late 1990s. you can see these are just projects that are being tracked by Woodworks. And so Woodworks, if you're not familiar, is a really great organization that promotes the use of wood in non-residential construction, trying to expand its use into other building types and uses. And it's a great resource for professionals. So they provide professional input, guidance to design teams, lots of resources available, white papers, case studies. But through their work and just through the the evolving building codes and everything else, you can see this rapid rate of adoption. And so while mass timber got a head start in Europe, for example, the speed of adoption, the scale is really impressive in the United States. Okay, so this brings us to our project, and I'm going to kind of talk through the premise of this as we move along. So you think about conventional floor systems. This is just one version that's illustrated here. Composite concrete filled decking. So this is typical, fairly typical in mid-rise construction, office buildings, other applications. It's pretty high embodied carbon, in particular due to the concrete content. This form of construction, depending on the construction type, if the steel requires a fire rating, then you're often using a fiber cement spray on that. So then that means that you're looking at drop ceilings. I'm sorry, it's a little noisy here in the background. So hopefully that's not coming through too much, but the drop ceilings and other systems to cover over the steel and the MEP systems. So you're talking about just a lot of complexity. You're talking about a lot of embodied carbon in the materials. And so with mass timber, you've got various options for the kind of floor and ceiling assemblies. One shown here on the left is you can build with carbon sequestering, mass timber. And then cover over the MEP systems with a drop ceiling of some sort, bulkhead. And so that's done quite a bit. So that adds, the cost and complexity of those materials. But it is a way to cover over all of that and get it out of sight. It doesn't present the full value of the mass timber itself, an opportunity to expose that and take advantage of that surface visually. But it is an option. In that scenario, as in most every application of mass timber, you're required very often to have a concrete topping layer. And that concrete topping layer is helpful for acoustics and vibration control. So we're going to come back to that in a moment. Shown here on the right is another alternative where you, as a design team, work to really think about and organize the placement of the MEP systems to where it's, visually acceptable, and then you expose all of that. And so, so that's great when you can do that. It really takes advantage of mass timber as a finished material. This is a project that was completed in 2018 in Portland, Oregon by Kaiser Path Architects. It's called Carbon 12 building. It's a residential building. It is it's all timber construction, except there's a steel framed brace frame core. And so, hold on. Hold on one second. You guys can just a little bit. Thanks. Sorry, I'm in the office, and so hopefully you all can hear me without too much trouble here. So what I'm showing is two options for the ceiling, right? So on the right-hand side is what we showed in the last slide, where all that timber is exposed. In this case, the architects working with the engineering team were able to kind of cluster and aggregate the MEP systems into the drop ceiling area, into this bulkhead over the kitchen. And so that shows both approaches right there in one slide. Another approach to systems integration is through the use of a raised access floor system. And so you all may be familiar with raised access floors. Maybe you've worked on projects that involve these. And so this gives you the ability to expose all of the timber underneath. You may have a sprinkler, automatic sprinkler system that's exposed underneath. But other than that, all of the mechanical ducts and whatnot could be included in the raised access floor. Maybe that it's a pressurized plenum up there. So this is great for sort of visual clarity and integration. This does still require the use of a concrete topping oftentimes, again, for acoustic and vibration controls, which we'll get to. This increases the floor-to-floor height for buildings, so there are various trade-offs associated with this, but it presents a great option for systems integration. This is a project completed in 2019 in San Antonio, Texas, designed by Lake Flato with Boca Powell Architects as the local architect. The timber was produced by a company called Structurecraft. And so this is a raised access floor system before the finished floor went on to it. They were able to use a 20 by 30 grid. This uses not cross-laminated timber panels, but dowel laminated timber panels over a glue lam frame. And so they're able to achieve a little bit of a longer span, a 20-foot span than you would typically get with mass timber. One of the things with CLT is you're typically limited with a 5-ply CLT system to somewhere between maybe 15 and 18 feet for the span, depending on the live load and the use case and the occupancy. For this, they were able to get up to 20 feet because dowel laminated timber is just a little bit more structurally efficient, but still limited to 20 feet. So hold that in your mind as we talk about our system. So what we have thought about and have been working on in Clemson for a number of years, and is the subject of this current project, is a hollow massive timber HMT floor cassette. And so this is built up with a 3-ply CLT flange on top and a 3-ply flange on the bottom, with glue laminated timber glue lam beams sandwiched in between. And so this makes a kind of hollow cassette. And so we see this as functioning in a similar way to a raised access floor, if you can provide access hatches at duct junctions and other kind of points of interest in the system. And so this does increase floor-to-floor heights, but it's, again, providing a lot of the same functionality as you have otherwise with a raised access floor. You see that there is the ability to expose the underside of the timber just totally without worrying about the visibility of the other systems. And then we have as a goal, with this robust, massive system with all this timber and the void space, is there the possibility of eliminating the gypsum concrete topping layer to better enable disassembly and reuse? Because as soon as that concrete topping layer, I'm going to go back to this, as soon as the concrete topping layer is applied, it means that that is married to the timber underneath it. So when you come to the end of the life cycle of the building or its components, you're not able to take apart the floor system and reuse the CLT panels or the glue lam. And so that's something that is a missed opportunity, because with these prefabricated panels, if you can think about a kind of circular economy, that would really add to the overall life cycle performance of these systems. Okay, so hollow mass timber floor cassettes have been the subject of some study at Clemson since 2013. It was first studied at that time by a team, including Graham Montgomery, who's one of our master's students. And at that point in time, they were focused on the connection behavior between the flange and the web connections. There were some digital simulation models. In 2017, the first full-scale test was performed, and you can see there that we were testing for a 40-foot span. So this was initially conceived as a long span built-up timber system. And so you saw in one of the previous examples a span of 20 feet. So we're doubling that with this system. And so through the testing performed in 2017, we were convinced that a 40-foot span is viable. There was some initial vibration testing as well at that time. Okay, so Brandon, back to you for the next few slides, just kind of bringing us back to our current project.
Yeah, absolutely. So as soon as we saw the call from ARPA-E for this Hestia program, we thought, hey, let's, bring the hollow timber cassette back and see if we can go beyond just, some strength tests and vibration tests, but think about it and how it might integrate into a building. and then perform all of the different structural, try to optimize the structural connections. You can see here we looked at cutting some holes in it so that you could access the different panels in order to run your HVAC, your plumbing, electrical through it. Stuck with the same 40-foot. And a big aspect of this, and partly because of our interest here at Clemson, but also because of the sponsor, was to look at and reconstruction. And Dustin did a very good job explaining why the concrete toppings are a problem for that. And so we've been thinking about this in different levels. You have the components, which are the individual CLTs and glue lams, the assemblies where they all are put together into the cassette, a structural bay, and then finally the whole office building.
There you go. And so that what's pictured there is actually a reference building, a baseline building that we've used as a part of this study. We actually got the initial layout from an example from the American Institute of Steel Construction. And so we modeled it with steel, and then we also modeled it with timber, a kind of conventional mass timber, as well as our unique HMT floor assembly. And so as part of this project, we've been doing comparative life cycle assessment studies. But here you can see illustrated, as Brandon talked about, the different scales of disassembly and reuse that we imagine as possibilities if we can eliminate the concrete topping. And so, Brandon, these areas of study have been a part of our project as well.
Yeah, well, and being able to take stuff apart at the end, little things like, even, do we use adhesives? Do we use screws? Well, if you use screws, you're going to be able to reverse them at the end. So these are all some of the structural considerations that we did, as well as vibration, which ends up being the controlling factor for these more so than strength. After we get done with these tests, we take them apart. Can you actually deconstruct them? What condition are they in? System integration we've talked about. Dustin's going to spend most of the time talking about acoustic performance here next. And then especially looking at the life cycle assessment, and I'll just reiterate a point there that Dustin mentioned earlier, is the end of life for these. If
Yes.
you grind one of these up and use it as, mulch in your yard, that's great. It's being reused, but all of that carbon that was in that wood is eventually then going to go back to the atmosphere. And so it's nice that it was delayed, but really to, lock in those benefits, you want to keep these timber components as buildings for as long as possible. Been looking at cost analysis, and then probably a lot of y'all are very interested in the code analysis, and Dustin will hit on that here as well.
Yeah, and then as mentioned, we were referencing as a vehicle for this study, we've been using this baseline building. It's a 3-story office building set in Atlanta, just for the kind of climatic factors. Type 3B construction, and then the structural bays are 24 feet by 40 feet. So that equates to 3 side-by-side HMT panels at a 40-foot span. And each of those panels, each of those cassettes is 8 feet wide. Okay, so moving ahead then, and getting into just the code of all this. Mass timber is how this relates to the IBC. Mass timber is accepted for use predominantly within type 3, type 4, type 5 construction. Types 1 and 2 are non-combustible. You can actually use mass timber for roofs within type 2 construction, but predominantly mass timber is confined to types 3, 4, and 5. And in the 2021 building code, type 4 construction greatly expanded. And so now we can build taller and bigger buildings with mass timber, depending on the extent to which the mass timber is encapsulated, or otherwise fire protected. It can be totally exposed in the case of type 4 heavy timber or type 3 construction. And you can see some of those details here taken from the IBC. You may be interested in, and you may have bumped into this if you've worked with mass timber or other wood frame timber structures, is this topic of concealed spaces. So it used to be that concealed spaces were pretty much prohibited in the IBC when it came to type 4 heavy timber construction. And so, but now in the 2021 building code, concealed spaces, whether they're plenum spaces or chases or whatnot, they are permitted within types 3 and 4. Types 3 and 5 construction. The presence of the heavy timber itself is sufficient as a fire stopping measure. And they're permitted within type 4C and type 4 HT in the 2021 IBC. Provided that these fire stopping measures are met. So for HT, you could sprinkler the cavity, which isn't always practical. You could fill the cavity with a non-combustible insulation, or acceptable for both type 4C and type 4 HT is encapsulation with a layer of type X chipboard. If you were ever to go to a type 4A or B, those are real big buildings, then you would be required to use 2 layers of type X chip on the in the concealed space. For our study, we were focused on type 3, and there's a lot of construction across the country with mass timber that falls into type 3 construction. Now, as you're familiar with the code, that prohibits the use of combustible materials in exterior walls, but because many of the buildings are post and beam framing, that's not an issue. You have a non-combustible construction, for the walls anyway. Okay, so let's talk now
Justin,
about acoustics. Yep.
I may just also add um, there's working on lots of different coatings, intumescent paints and things.
Yes.
And I
Yeah. Yep.
think
Right.
by the letter of the code, my understanding is they don't necessarily count as, encapsulating with gypboard. That said, depending on what jurisdiction you're in, I'm aware of some projects where they've, used that. And
Yep.
so anyways,
Yeah.
just
Yeah.
there's,
Looking at coatings, that's a good point.
yeah, there's other things that are out there and
Yep.
coming down the pipe,
Yep.
just to be aware of.
Fantastic. Okay, so we'll turn our attention then to the building acoustics and the acoustic performance. Acoustic performance in buildings really falls into two categories. One is airborne sound, and the other is structure-borne or impact sound. So some of this you may be quite familiar with, some of it it may be new to you. The airborne sound is typically classified with a rating, what's called an STC or sound transmission class rating. And that's measured through a standardized test in a laboratory setting. And the IBC in Chapter 12 specifies that dwelling units and sleeping units have to achieve an STC rating of 50 or higher. And that's really the most stringent case prescribed by the IBC. And it's not easy to achieve that. And so anybody on the call that's worked with multifamily construction knows that that's a challenge. For structure-borne, it's measured typically through IIC measurement, impact insulation class, which again is based on a laboratory test, and you're required to achieve a rating of 50 or higher for the same use cases. For both cases, it's worth noting that the IBC permits ratings of 45 or higher when field tested. So there's a separate set of ASTM test standards for field testing. And rather than being classified as STC, the airborne sound isolation is called NNIC, Normalized Noise Isolation Class, but it's airborne and you have to achieve a rating of 45 or higher. And then you see NISR for the impact sound, and again, a rating of 45 or higher. So our key driving question for the acoustics piece of this project is, can our unique HMT floor assemblies, whether that's a bare assembly or an assembly with carpet and other finishes applied, other layers, can we achieve uh, um, floor assemblies that meet or exceed code requirements for sound attenuation without needing concrete toppings, thereby reducing the carbon footprint of the floor assembly and also enabling the future disassembly and reuse of the components in a circular economic scenario. So how is sound measured and studied, whether it's a field test or a laboratory test? For airborne sound, what you're doing, and for structure-borne sound, is you're testing floor assemblies within a two-story test scenario. In a laboratory setting, it's a test chamber. In a field study, it's one apartment above another. And so what you do is the upper room is called the source room, and that's where you're generating the sound. So that's where the sound source is. And then in the room below, that's the receiving room, and that's where you're measuring the sound transmission. For airborne sound, you're producing like a pretty high decibel level, what's called pink noise with um, a amplifier like you see here and a dodecahedron speaker. And so it's like a non-directional, it's like kind of an omnidirectional noise. And then for impact sound, you're using a standardized tapping machine like you see here, which has these pistons that go up and down and these hammers on the bottom of that. And so it applies a tapping on the floor at a prescribed and standardized frequency and force. And so then again, you're measuring down in the receiving room. So oftentimes this is done in industry through third-party testing labs. So this is a lab actually that belongs to Maxon. Maxon is a company that makes, ironically, gypsum concrete toppings as well as acoustic membrane layers. And so we thought about taking our system for this project and sending it off to a testing lab and have them test and see what our performance is. But on the one hand, we knew that we were going to be doing a lot of iterative testing, adding, different layers of flooring on to kind of see what the effect is. So we wanted to have a lot of control over that and flexibility. We also wanted to just make an investment into our laboratory, into our students, and our capacity here at Clemson. And so we decided that we would design and build and then operate a two-story test chamber here. So you see a graphic showing our two bays of our structural lab, what we call our built environment lab. So we had designed this chamber to where it could break into two halves. The upper walls are hinged and they can collapse down. So we can move the parts of this chamber between our low bay space and our high bay space. The low bay space is shown here toward the bottom of this image, and the high bay space is shown here with the two-story chamber kind of resting in the corner of it. And so this provided a number of opportunities for us. One is it was a great opportunity for us to really get to know intimately, all of the details of the testing for ourselves. It allowed us to invest in a kind of infrastructure, acoustic testing infrastructure, that means that we can go out and pursue other grants and partnerships beyond this project. It also meant that we could turn this into a teaching tool. And so lots of students were able to participate in the design and in particular the construction of the sound chambers. So they learned about light frame construction, double stud walls, high performing, acoustically performing wall, floor, and roof assemblies. And so this whole thing came together. And here you see it in its place with our rolling gantry crane above. We have the lid is, all the walls and the permanent floor system are all really robust, acoustically really dense. We used layers of sheetrock and homosote over resilient channels. And so the idea is to prevent sound from coming in or going out through the walls and other permanent construction. You really want to isolate the sound movement to the floor specimen that you're working with. And so if I go back for a moment, you see here that there's this big hole that's cut in the floor. That's where the experimental floor assembly would be put into place. And so you can see all this robust concrete construction all around. And so the idea is that any sound generated in the source room is only able to go through the tested assembly into the receiving room. So that's what we did here. Here's a diagram showing our layout as well as a cross section through one of the HMT floor assemblies put into place within our chamber. You can see some of the details of the wall materials. And so just a quick couple of notes about how you test this. So the first thing that you do is you go into the receiving room and you take a first set of baseline measurements where you're measuring background noise, interference. It's noise, from the ambient environment. And so you do that so that you can zero that out. You can take that out of the measurements that are later recorded. The next thing that you do in the receiving room is you blast some sound. And you may do this. I'd have to refresh on my on my procedures here. You may do this as well in the source room, but basically you blast sound and you measure the decay rate. So how long does it take for the sound to actually decay out? And so that factors into the calculations and to the whole process of coming up with these ratings. The next thing that you do for airborne sound is you actually go up into the source room and measure the decibel level of the sound in the source room. And you do that at various locations. You have various speaker locations for all of this. And then after that, you would go downstairs and then measure how much sound is coming through the system downstairs. And the net difference is the sound that's transmitted between the source room and the receiving room for airborne sound. For the tapping sound, you don't have to take any measurements up in the source room. You just take measurements in the receiving room because the force of that impact is applied directly to the floor specimen. And because it's a standardized tapping machine, there aren't any preliminary measurements that are required. You're only measuring at various spots downstairs in the receiving room how much sound is coming through that system in terms of the impact sound. Okay, so the first thing that we had to do in order to make sure that we were on the right path for all of this is we had to use some kind of control floor assemblies in order to test and measure to what is expected data, published data, available data in order to, basically we're comparing to data that's out there that has been compiled by professional laboratories, other researchers, to make sure that our setup and our procedure, that everything is yielding results that are to be expected. So once we could validate through that process, then we were ready and able to move on to our own experimental floor system and the related testing. So this is one of the control floor assemblies, used I-joist construction. See that going into place here. You see the top walls that fold down in the whole chamber. and then from inside the receiving room below with that control floor above. And then ultimately we were able to validate our setup using just a bare 3-ply CLT floor. And the data was unpublished on this, but we were able to work with Maxon. They had actually tested a bare 3-ply system. So they provided their data, and then you can see that in the green column here. And then we were able to do a couple of tests of our own. And we were satisfied that the airborne data, and by the way, the decibel levels for sound transmission, they're measured across a range of audible frequencies, as you see here. And then all of that is averaged into the overall ratings. So long story short, we demonstrated consistent data with what Maxon had done in their professional lab. So we felt like we were ready to move forward. We felt like we had validated the system. And so then ultimately, these were the variations of our hollow mass timber system that we tested. So we tested the bare assembly first. And the bare assembly, we tested these at a length of about close to 20 feet. So while we're interested in the structural capacity and the span of 40 feet for this acoustic testing, we just kind of shortened it down based on the footprint, the volume of our acoustic testing chamber. We worked with a 20-foot span, 8-foot width. I should note that throughout all of this, we actually use the field test standards and measurements rather than the laboratory-based measurements from ASTM. That was based on the advice of several of the professional acousticians that we reached out to. We just weren't able to build a sound chamber that had a big enough volume to technically meet the requirements of the lab testing for the STC or ISC rating. So we were going instead with the field test measures. So here you see that bare assembly being craned into place, and then you see a view on the right from the source room and then downstairs in the receiving room. Next assembly that we tested after that, so we did this bare assembly just to get a sense of the baseline. You know, what kinds of ratings would you get just with the system right out of the box? Next, as we added carpet tiles, interestingly enough, the carpet tiles came from a company called Interface, and it featured a carbon negative backing, which is really great. After the carpet tiles, we took all the carpet tiles off and then used an acoustic mat from Maxon, plus 2 layers of 3/4-inch OSB subfloor. So the acoustic mat, just like with the carpet, it serves to decouple the impact sound from the structural substrate of the mass timbers. That's really important for impact sound mitigation. After that, the next specimen that we tested is with a single layer of OSB subfloor over the acoustic mat. For each of these tested assemblies, we ran 2 tests and then averaged the results. Two sets of tests and averaged the results. Next is we kept the same kind of general system there with the acoustic mat and the OSB, but we cut in the access hatches as well as the duct penetration holes. And then finally, we kept all of that from 3.5, but we added a blow-in cellulose insulation, which is non-combustible. It has some properties that help, potentially with acoustic sound attenuation, but also it's one of those fire-stopping measures that's acceptable for Type 4 HT construction. So we were interested in that synergy. And so just to summarize the results here and to bring us in for a landing, here you see the overall results for airborne sound transmission. So right out of the gate, the bare assembly provided a airborne sound rating of 45, which met our requirement. And then the other assemblies
Dustin, could
only added to that. Yep.
Could you just remind me, probably for everybody else, I'll ask the question. I know one of these you want to be lower and one of them you want to be higher air on these graphs. So if you could just
Yes.
orient
Okay.
me a little bit. Thank
So that's
you.
good. So this the airborne sound is classified based on transmission loss, and so that's the net. So it's the decibel level measured up in the source room, and then you subtract out then the decibel level measured down in the receiving room, and so the loss is reflective of how much is transmitted. So you want the sound transmission loss to be high. Okay, so all of that then is averaged into the NNIC ratings that you see at the bottom of that table there. I'll have a summary table in just a minute. Okay, now here's the impact sound. Now this one, there's one outlier, okay, and I bet you could guess which one it is. It's the bare assembly. And so for that bare assembly, naturally the impact sound just moves right through that. It moves through the solid material. It moves through the connections, okay? By the way, for the impact sound, when you set up that tapping machine, the test standard requires that you position the tapping machine in 4 different ways. And so it's positioned right in the middle of a floor panel, then you move it to the side by a foot. And the idea is that you're going to be in between joists, versus on top of a joist. Then you turn the whole a tapping machine 90 degrees, you turn it 45 degrees. There are all these different things. So the idea is that you're getting a kind of overall profile of the acoustic performance of your floor assembly. So we modified that a little bit. We ensured that one of the locations for the tapping machine was directly over one of the glue laminated web beams within our HMT assembly. And probably through the influence of that, as well as the other locations, the bare assembly, did not achieve the required sound isolation that we would need for impact sound. And that was to be expected because the sound is able just to move through those rigid connections. But as soon as you apply carpet or an acoustic mat, and you decouple that sound energy from the timber below, then you have really, really good results. And so in this case, for impact sound pressure level, because it's a direct measure of sound coming through, you want the results to be low. So all of those lower graphs here, lower curves, those are ideal, and those are the ones that are equating to NISR ratings over 50. Okay, next is just a summary here showing that really every one of the assemblies, including the bare assembly, met or exceeded our target of 45 for the airborne sound transmission and the rating rather. And then all of the assemblies except for the bare assembly exceeded our target rating of 45 when it came to impact sound. Okay, so one variation that we've looked at across the whole project is looking at a variant of the HMT cassette that includes kind of a shortened or truncated bottom flange. And so in this case, the idea is, and we've been working with an industry advisory panel throughout the course of this project. And so those are contractors, they're MEP specialists, architects, engineers, fire code specialists, et cetera. But through some of our conversation with them, as well as other presentations we've given, we've learned, okay, yeah, it's great, this application where you have top-down hatches, but there may still be some application, some desire to have bottom-up access, more conventional access for installing and maintaining the MEP systems. So what would that look like if there was just this cavity space in between the panels? And so that's what we're showing here. And so we've done some testing on this acoustically. And you can see that in the bottom sketch here. That shows the access hatches and the potential locations of ductwork and other systems. But shown in orange on the bottom sketch there is just a lay-in acoustical ceiling tile. And so we mocked that up in our test chamber. And here you see the results. So the bare assembly with the truncated flange and the ceiling tiles covering over the resulting opening in the ceiling yielded a airborne sound rating of 41 and an impact sound rating of 37. As soon as you add carpet, the carpet doesn't really affect the airborne rating much, just because the carpet doesn't add much mass, but it affects the impact rating quite a bit. So it jumped up to 49. Airborne is still, at 42, which is below what we would like to achieve per the building code. Then with the acoustic mat and the added mass and density of one layer of OSB, you get up to 45 for both. So this is not entirely conclusive. I mean, there's some limitations to what we can test with this in terms of what we can really sort of reproduce in terms of the passage of the sound through those openings. But we're encouraged by this. It's still just the mass of the system is working for you. The worst case scenario would be if this guy in the sketch on the upper right-hand side, if he were standing right above that kind of central void and walking around making a bunch of noise, that would be the worst case scenario. And the sound transmission through that void, even with the ceiling tile, probably would exceed what you would want for the most stringent use cases. So more to be determined on that. Just some resources for you if you're interested when it comes to mass timber and acoustics. Woodworks has actually just begun a couple of months ago this very, very detailed database that you can register for. It's free to register and gain access. And so this is for fire rated assemblies as well as acoustic rated assemblies. And so if you go into that, you can see that it's, a whole range of tested assemblies. It gives the kind of overall ratings for airborne and impact sound attenuation. And it shows, all the different products in those assemblies. So this is akin to like a UL manual for all the fire tested assemblies that you're well familiar with. But this is for acoustics. And so this is a really great resource. One of the things that's really still a challenge in the industry right now, something to be addressed and really understood and overcome, is the influence of flanking sound. So sound that goes up through a ceiling. You can have a very robust wall whose, all the layers of the wall construction are in and of themselves sufficient for limiting the transmission of sound from one unit to the next, side by side. However, if the sound is able to get up into the floor system and flank over the wall, then that can undermine the acoustical performance of the wall itself. And so for mass timber, this is really an area that needs further study. There was a study that was done by Arup engineers several years ago where they looked at just a bare 5-ply system over a acoustically rated, wall, demising wall. And they found that the flanking sound, the sound energy just moving through that panel and over the wall was not insignificant. And so they came away, recommending that you actually create a structural joint, basically cut the panels, have 2 panels come together at a seam above a acoustically rated wall. That's impractical, though. I mean, think about it. If you if you had to limit your mass timber panels to just the spans,
Are we experiencing technical difficulties? I lost Brandon and Dustin. Okay.
I'm still here, but just turned off my video. I think we probably just lost Dustin in the slides. I happen to think that was his last slide anyway, so
Okay, well, maybe he'll hop back on.
yeah. Yeah, he and I went through them a little earlier today, so I can mention a couple things we wanted to wrap up with. One being that we're gonna release a technical guide on all the work that we've done. So it's gonna have structural, acoustic, building code, LCA, deconstruction. It's gonna have all of that in one package, and we're gonna hopefully by the end of this calendar year, we will release that for everyone. The other things I would say is we have this new testing ability here at Clemson to test these acoustic assemblies. But we also, that same equipment, we can go on the road with it. And so, if there's a building that y'all have that, the owner's interested in doing some sound transmission measurements, that's something that we can do. Now, the good news for all of you is that since the federal government purchased all this equipment for us through this grant and this research, we're not allowed to charge anyone for the use of that equipment or that facility. Now, there's still some costs associated with our time and mobilizing the chamber and things, but yeah, we have this cool new capability, and we've been on the road with it already and had some good success with that. So I guess that was wrapped up what we were going to present. And if we lost Dustin, I'm glad it was really quite close to the end. I can try to answer questions, but it might be rather poor relative to what Dustin would do. But I can make myself available here for a few more minutes.
Anybody has questions, I can unmute you so you could ask. Ah, see Dustin's come back.
Ah, he's back. Good. Dustin, I told them about our facility
Great.
and that we're going to have a technical guide coming out. And so it was just, whatever
Perfect.
questions they might have.
Perfect. Yeah. So the technical
I'm so
guide.
glad you're back because I was worried I might have to say
No,
something
thanks.
about
Sorry about that,
architecture.
everyone. We just lost connection here.
Yeah.
So the technical guide that we're covering, the following subjects. We're really aiming to have this be a resource pertaining to our HMT system, to be a helpful resource for building design teams, owners, developers, as people are thinking about this system and its application and whether it's a potential system for their projects. And so you can see the list of subjects here, just the overall premise, the review of the HMT system and features, code analysis, where this system will be applicable within the building code, which construction types, structural performance, constructability, MEP, integration, strategies for that. We've, as I said, have been working with MEP engineers, kind of thinking through some layouts with respect to our baseline reference building, acoustic performance, life cycle assessment, et cetera. So one question that we have for you, you all may have some questions for us naturally, but we also just would love your feedback as you sort of think with a couple of minutes that we have here, or otherwise just getting in touch with us after the fact. What do you think would be particularly helpful within a technical guide like this that would answer the questions that you would have? Maybe any holes that you see in the content that I have here in the slide, something that would make this a useful technical guide for you to help you learn more and consider this system where you would want a longer span, where you'd want the benefits that we've described. So anyway, that's where we were going to leave off, and
Dustin, there's a couple questions already arrived in. I can read them to you here. Chris Bonner asks, I've heard in the past that there were sometimes, in quotes, acoustical events that happen as the building ages. Maybe the general shrinkage of wood has given way to a better assembly process. I don't know if you've heard of these acoustic events or aging effects. I have not. And did we lose Dustin again? Okay, I'll go on to the next one, which is I've been in one building in SC that has mass timber elements. What percentage of all buildings use mass timber in recent years? I can't speak to the percentage, but I'm just amazed at how quickly this technology has grown. I mean, you all know we work in an industry where new technology takes a long time to adopt. It takes lots of different testing and things, and to go from just a few buildings a few years ago to where we're at now is quite impressive. I can say just right here on the Clemson University campus, the new forestry building is going to have mass timber. The new the Quattlebaum Center. So I think I can think of about 3 or 4 buildings just in the last few years on the Clemson campus that have mass timber. And some of the feedback I'm getting as a structural engineer from the companies is they want more students that can help them and know about mass timber with design. So we're certainly trying to catch up as structural engineers on this as well. Oh, and then Dustin just texted me. Sorry, I lost again. Can you field the questions? I did my best. So I don't see any more coming in. Stephanie, I guess back to you.
Thank you, Brandon. That was fantastic. Thank you, Dustin. I've recorded this, so if you'd like copies, I can send those around. Your learning units will be recorded in the next few days, and I'm sure if I'll send contact information to you guys if you want to reach out to the group, follow up with any of your resources. But we appreciate you being here and sharing that great webinar with us and answering our questions. Any last questions, folks?
Oh, how about cost comparison to standard? Yeah. So when we priced out the steel and concrete building that we based our timber design on, and my best estimate is you're going to be paying a premium right now for the mass timber, somewhere between 5 and 10%. And I would think that will come down as the capacity in the United States and North America for mass, well, I guess with tariffs, who knows? But with as the capacity in the United States to produce mass timber increases. So, but yeah, right now it's at a premium relative to the traditional steel and concrete with a drop acoustic panels.
Well, there you go. Keep up the good work at Clemson. Thank
All
you.
right, thank you. And as our technical guide comes out, we'll send the link to you, Stephanie, to distribute to all the South Carolina AIA members.
Oh, great. I'd love to share that. Okay, everybody, we're all set. Have a great day. See you next time.
Thanks.